We have pictures of you and presentation. There is nothing from. I'm really curious. I'm afraid based on what I saw at the last meeting. Just like, show of hand polls in the rooms or during a technical meeting of who's gonna go. Maybe that's changed, but I never.
About 10 people. Yes, that's
perfect. So Bharat, you're sure. 1 minute. Sure. Okay. I like this. Hey, good afternoon, everyone. Welcome to this CAV seminar. Today, we are welcoming Professor Vincent Tournat. He's a research professor at CNRS at the Laboratory of Acoustics at Le Mans University in France. He has his PhD in 2003 in nonlinear acoustics and granular materials. And in 2004, he was a postdoc at the Hokkaido University in Japan, working on laser picosecond ultrasonics. And after he had a position at CNRS, and he establishes 2 research groups on acoustics and of granular materials and laser ultrasonics. And he was also developing other research topics on ultrasonics, non-destructive testing and acoustic metamaterials. And recently, his research focuses on nonlinear waves and flexible mechanical metamaterials. And from 2007 to 2022, he is the head of the acoustics and mechanics of materials research team with more than 50 people. And he was awarded several prizes, including CNRS bronze medal in 2010 and silver whistle from the International Commission on Ultrasonics in 2013. And he's now director of the Institute of Acoustics, a graduate program created in 2017. He was also awarded the National Level Graduate School. And he's been recently regularly invited professor in several countries, in Japan, in Chile, in Spain, in USA. And he's now a visiting research professor at Harvard University since September 2022. And Vincent, welcome, and we look forward to your presentation.
Thank you for a nice introduction. Too nice. I'm very glad to be here. Thank you for the invitation. I'm very glad first because you are a lot in the room. I know also people on Zoom. I'm very glad for several reasons because that I can tell you. I've heard about the Penn State graduate program in acoustics for a long time already. I've always thought that we can do something together. So I hope my talk will give you this this motivation to work more together and interact. Another reason is because the first time I came to the US in 2005, I came in Penn State for a conference. So I'm glad to be back almost 20 years later here in State College. And so yeah, and with this talk, I would like to, share some recent results that are like very important for me. They are most probably a bit specific and don't give the full impression of what we are doing in Le Mans University and what I'm doing. So maybe before jumping in the presentation, scientific presentation, I would like to share with you 2 or 3 slides about my institution and some maybe you'll see some parallels between your program and our program. So I'll come back to that, but maybe I'll start with locating the institution where I am. We are located in Le Mans. Le Mans, the city is a small city in France, the west of France, not far from Paris. And it's famous for maybe only one thing, which is the car race, 24-hour car race of Le Mans, which is existing for a bit more than 100 years. I think it's the 100-year anniversary recently. So there are not only cars in this city, and it's only once a year in June, but there is also acoustics, and it's a bit, I think, of a specificity of the city as well, because we are in a small university, but we have a rather large acoustic program, and everything is within what we call the Institute of Acoustics Graduate School, where we have a research lab, which is basically a department, and some programs, master programs, undergrad programs. About 500 students in acoustics are studying there, 300 being undergrad and 200 master students or engineering students. And we have about 70 PhD students in the lab. We are also about 60 faculty in this acoustics institute, working on acoustics, on various aspects of acoustics. And what I want to say today is that we are very interested in international collaboration and mobilities. And so we have funding for sending students, sending professors, or receiving students and receiving professors for research visits of like a month or 2, or internships for students or visits. So if anyone is interested to talk about that after this talk, we can talk more. Just last slide to try to give you a very quick overview of the topics we work on. So we are organized in 3 teams, but I split it a bit the topics to be more specific. So we have historical activity on the acoustics of porous media since the 90s. This is our core specialty, I would say. Obviously for noise control and things like that, vibration control. Laser ultrasonics, so how to generate and detect ultrasonic waves with lasers, waves in granular materials, acoustics and elastic metamaterials, NDT with ultrasonic waves, thermoacoustics. I think we had a few collaborations with Stephen Garrett in the past. Microacoustics, macro systems in acoustics. Transducers, it's a big activity nowadays in the lab. Design of transducers, loudspeakers, microphone, and so on. Lots of activities also with contracts concerning vibrations, acoustics for car industry, transportation, and so on. And aeroacoustics, so also with many industrial applications. And to attract some few students, we have musical acoustics too. I mean, it's not only for that, but it's the nice entrance door for. I started like that, and I was pushed to do something else which actually I liked a lot. So yeah, this is just to give you an overview. I think there are like lots of similar topics than you have here. So quickly coming back to the title of my talk and jumping in the scientific presentation that I want to share with you. I will talk about a topic that is of interest to me for the last 6-7 years. When I first started to interact with Katia Bertoldi in Harvard and Jordan Rane, who was at Harvard at that time and with no faculty at UPenn. And we have this project that we like and we work on it together. It's about how nonlinear waves, nonlinear mechanical waves propagate in flexible structures, flexible metamaterials. And to give you an example of the structures we've studied, these are these origami rubber sheets that are laser cutted, so designed in a specific manner. This is an example. So they can be made with properties coming from their geometry. So they can be bistable, stable in 2 different states, open or closed. And this can be useful, for instance, for deployment, reconfiguration of a medium. There are also like other examples of these flexible metamaterials. The well-studied rotating square structure or a rubber plate with holes in there that you will see can be seen as a rotating square structure, squares connected to the neighbors. And this offers new mechanical behaviors like oxidative behavior, micropolar behavior. And other like fabrication methods allowed also to go to even more advanced structures. So this is direct PDMS printing, and once again, through the geometry of the structure you print, you can go to, for instance, in this case, bistable systems that are good for absorbing shocks. And other examples that we will see in the talk we studied. So assembled structures made of rigid and very flexible units, such as Lego pieces for the rigid part and plastic shims for connecting them that are very flexible. So these are the structures that we find interesting. I used to study actually waves, nonlinear waves in granular systems, and nonlinearity in granular systems obviously come the contact between the grains. And one a bit annoying thing with these systems is that we cannot change the contact properties really easily. I mean, this is here, we have to model it. It's very complex actually, down to the nano level of like rugosity and water bridge formation and so on. So it's really a mess. And I was desperate to find a system where we can control more the nonlinearity seen by the waves propagating there. And these structures are mostly nonlinear because they deform strongly, and this nonlinearity is driven by the geometry of the system, not by the elasticity of the constituent. So this was very appealing to me, and one of the first results that was very inspiring is quasi-static actually. So it's this rubber plate with a spherical with holes in there. And when you look at the stress-strain relationship, you see a strongly nonlinear behavior when it starts to buckle. You have this inflection. And the idea was, can we exploit that for waves? Can we use this type of nonlinearity for waves? And you can see the structure, as I mentioned before, as a rubber plate with holes. But if you look at the inverse, you see also squares that rotate and that are connected to the neighbors with thin ligaments that deform mostly. So we call them these structures rotating square structures, and we try to study that a bit in depth with the following questions. Can we propagate waves in these systems? Do they support waves, and especially nonlinear waves? And then if yes, and this is the case, can we, by changing the geometry, by changing the design, can we control the nonlinearity of these waves? The nonlinearity of these waves? Can we control these nonlinear waves? That were the questions we asked at the beginning. So I'll show you some results in three parts. We'll show you maybe the first result we obtained. It's a bit historical, 6 years ago maybe, but that will help me to show how we tackled this problem and the methodology we used in the following. Then I'd like to talk to you about transition waves. I'll tell you what it is for those who don't know later. And finally, very recent results about going non-periodic. So designing systems that control waves, but that are non-periodic. Okay, so let's start with the first part about how we started working on this problem. So we started with this structure, which is a rotating square structure, as the green rubber that you've seen, the green polymer you've seen before. It's 3D printing PDMS, and we started with printing squares connected between them with thin origamis. And obviously, to see wave propagation, we tried a bit elongated sample. There are many problems with that. You have to deal with the in-plane rigidity, out-of-plane buckling, etc. We ended up actually working with this sample, which was longer, with an initial rotation of the square, so the design has been a bit changed, and an added mass in the middle to improve, to enhance the inertial effects for the wave propagating there. And so we looked at the waves propagating in this direction. It's about like 1 centimeter thick. So it was sufficiently soft in plane to avoid buckling out of plane in this case. So this is a typical experiment that we've done. Very simple to start with. We have an impactor here, a hammer, a holder, and this impactor sliding in the holder. And what we see here with a fast camera is if you look carefully, it's a pulse propagating in the sample. So we were able to generate a pulse. We can control a few things in this setup. So we cannot control beforehand, but at the end, when we process the movie with digital image correlation, we know what we input and we see the wave propagation. So a typical example is this. So this is an experiment. At the top, you have one impact, at the bottom, another impact. And if you look at the spatial temporal plot of what is happening in the system for the horizontal displacement, you have a front propagating and reflected a bit. If you apply a different pulse, you have a steeper slope, for instance, and you have propagation in the system. So this is the displacement, horizontal displacement of the units as a function of space here, and you see at different times a wave front that is propagating, a wave propagating. What was striking at the beginning when we saw that is the very stable nature of the pulse. So we would apply a wide frequency band pulse, large amplitude, and it will be rather with a stable shape along propagation. So we thought, oh, maybe there is a signature of nonlinear propagation in there, fully balanced with dispersion, and actually a soliton propagation in there. So stable shape pulse in the system. So to try to show that or to model that, we went to modeling. And just for illustration, when you look at the FEM quasi-static compression of such sample, what you see is that most of the deformation occurs at the thin ligaments between the squares, which is rather obvious. And when you have a plane wave propagating the system, you expect that the displacement will be mostly horizontal, and we see rotation of the squares. So this helped us writing the problem for this for the modeling that we wanted to do, and take some assumptions. So we assumed that the system was periodic. We would consider one mass connected to 4 neighbors. This mass can rotate with the angle theta and can move along the horizontal axis with the displacement u. And we modeled the ligaments with springs, effective springs, linear springs, a longitudinal and a bending one, a torsional one. In this case, because of the symmetry of the wave and the system considered infinite, we don't have shear excitation actually, so we neglected this this coupling. So when we describe with this lump parameter model this system, we assume periodicity. We actually come up with 2 equations for motion equations for each mass, rigid mass. So each square is considered as a rigid mass. 1 equation of motion for the displacement, the acceleration in displacement, and 1 equation of motion for the rotation. They are coupled, and we have a number of them because we have a number of masses. So just to show you very quickly the methodology, I don't want to go too much into details. These are like how they look, these equations, where when we use normalized variables, time, coordinates, and so on. So rather complex, but what we can see from it is the following. So part of it is just the equation of a chain of masses and springs for the horizontal displacement. Part of it for the rotation is equivalent to a chain of coupled resonator. Fine, linear. And all the rest, all the terms that remain are coupling terms. We see theta here, we see some u somewhere here. So these equations are coupled. They are nonlinear because of this cosine and sine functions. And so we can, from that, deduce that the nonlinearity in the system is coming from the rotation of the, it's geometric, and it's coming from the rotation. So there is no material nonlinearity involved here, like at the micro level. Fine. So we can solve that actually numerically. We can just integrate on the computer these equations. Fine. We have a numerical solution, but we can also find analytical solutions that are approximate. I won't go into the detail, just give you the few ingredients to do that. So when we plot the things at the end, this is space, and this is the displacement, this is the rotation. When we compare the analytics and the full numerical integration of these equations, for one case, we have a very good agreement. And what we did for the analytical model is to simplify these cosine and sine functions and take only the first nonlinear terms of this, expand these functions. We assume we went from the discrete space to a continuum space, so we assume rather long wavelength in the system. We take only the first order dispersion terms as well, and then we looked for propagating wave solutions. With all this, we actually can modify this full discrete problem, a nonlinear discrete motion equation problem, into a single nonlinear Klein-Gordon equation that looks like this. So this is the propagative term for theta, the angle, dispersion term, and the first order quadratic term of nonlinearity. And we have a coupling equation which couples theta and u. They are connected directly. So this equation is known to have a soliton solution, pulse solutions that are stable along propagation. So even if it's nonlinear and dispersive, and there are analytical forms for that. And this is what is plotted here. So this solution is actually a vector soliton solution. Vector because it has 2 components, u and a theta, that are coupled. So it's a vectorial wave, and it's a solitary wave or a soliton because it's a stable solution in the nonlinear and dispersive medium. with some properties. For instance, we have here the width of the pulse, the amplitude, and the velocity that are all coupled, and it's coming from the equation, the solution form. Well, so we have a sort of agreement between the full numerical discrete model and the analytical approximated solution. But now we can also input the experimental input that we have in each experiment in the numerical code of integration to check if our model, discrete model, is a good one for our experimental system. And this is what is shown here. We have the displacement amplitude, the displacement which is shown here as a function of space. And at a given time after the impact, we see different waves coming from different initial impacts. And in symbol, you have the experiments, and in line, you have the numerical evolved solution after the experimental impact is inputted in the code. And you see good agreement after propagation in the system, showing that we have a code, we have equations that are representing what we see in experiments. And this is the same for single pulse, but at different times in the system. We see that it's evolving similarly, except that when we feel the right boundary of this. So with this methodology that we use like over and over on different problems that I will illustrate later, we could predict and observe this vector solitons. And we have also direct formulas with these analytical solutions, linking the characteristics of the waves to the characteristics of the medium, the geometrical characteristics, as the initial angle of rotation of the squares. This is a geometrical parameter that we can choose. This is an inertial parameter here, the mass and moment of inertia. This is connected to the width of the coupling. This is an elastic rigidity of the ligaments. So we have a rational way to tune the system in order to obtain the right properties for the waves. Fine. So now maybe in a more illustrative manner, I will go through other problems we've treated with a similar methodology. So for instance, we went 2D. So this is the exact same system than the one elongated like that, which was quasi 1D. But here it's 2D, and you have an impactor here that we can move a bit, or actually move the disk, we rotated the disk, to look at propagation along different angles in the system. So once again, this is the experiment. We see with the fast camera something in there. If we compute the movies of with digital metric correlation, this is what we have. When we excite here at angle 0 degree horizontal, 15, 30, or 45 degrees, which covers more or less all the orientations of wave propagation in the system. What we see is a stronger anisotropy. It doesn't behave the same when the wave is excited at different angle. What we could show is actually that at 45 degrees, we have a very interesting structure here. You can forget about the surface waves that propagate around. This is something we study later, but in the middle, you have a pulse, which is with a stable width along the propagation, but also in the lateral dimensions. And this is what is called a spatio-temporal soliton. I mean, it has all the characteristics of a spatio-temporal soliton, where not only the dispersion and the nonlinearity are perfectly balanced, but the diffraction and the nonlinearity are also perfectly balanced. So this sound bullet, as it's called, is propagating without diffraction and without dispersion in the system. Okay, I won't go into the details, but we can also numerically integrate the motion equations of the system and show that we have a very similar behavior than in experiments. The model here in this case is 2 degrees of freedom in translation and 1 in rotation. So 3 degrees of freedom. I don't have enough space on one slide to show the equations. So anyway, I don't. Okay, so just a short summary of where we are right now. As I told you, we can tune with this platform the nonlinearity that is seen by waves, the dispersion, etc. We can, I didn't show that, but we can also apply some static stress to modify the properties for seen by the waves, and the linear and nonlinear, and tuning the geometry of the system that's initially fabricated, printed, or assembled. We can actually access different types of equations and everything in between. So we have, and all these equations are nonlinear Klein-Gordon equations. They have analytical solutions in the form of solitons, so of various solitons. So this is where we are, and maybe if you are interested, we published 2 years ago a sort of review paper on these things, where we gathered the work from other teams and other work we've done on I told you about assembled Lego chains. They are very convenient because you can easily change one ligament, make it harder, induce a defect, etc. And we could show that, for instance, you can build a diode, an acoustic diode for the solitons. So if you impact from one side, it will go through. If you impact from the other side, the same thing. It will be reflected by a well-designed inhomogeneity in the middle. And what you see here is that actually this way of modeling things for the rotating squares is actually very ubiquitous. It works for very different systems of like bended plate coupled together, origami units, tensority units, or even some slinky here. So if you are interested, you can have a look to that. Okay, let me switch to the second part, which is less. I will be more high level in this part, showing you examples of what we've done, and you can consider that the equations we've solved are like, and the methodology we used is very similar. I would like to talk about transition waves. This is something that I find very interesting. Transition waves, they actually exist in so these are examples of transition waves in multi-stable systems, bistable, for instance. So these systems, these kirigami rubber sheets, they are by the type of cuts that are made there can be stable in an extended state and a compressed one. So the extended one is the purple one, and the compressed one is the yellow one here with the movie processing. And what you can see is it's a real-time video each time. What you can see is that when you push with an indenter some few units to switch state from the extended to the compressed one, after a nucleation of like enough unit in the other state, then there is a sort of avalanche, a front propagating of that changes the unit state from one state to another. So these transition waves can be useful, for instance, to reconfigure a whole sample from one boundary. They can be yeah, they are quite some people mentioned, I have an example later, but they mentioned that it can be used for energy harvesting and so on. So what we've done here is actually to also put some effects to see if it could block these waves, if we could control also the sequence of switching of the units, things like that. So what we maybe if we come back to a more simple system. These transition waves, they also exist in 1D, and this is a very nice example of a system that supports them. The system is like this. We don't see well on the movie, but it's like this. buckle beams that can be on to the left or to the right in two stable states that are coupled together with springs, and you have a little mass in there for inertia. And what you can see is that when you push the first unit, then it triggers the transition waves where all the beams go from the right configuration to the left configuration. So they change states. The potential energy of the system of each unit is actually with 2 minima, and you go from one to another. So there are many examples of these. For instance, buckled plates connected with or coupled with magnets. When you switch the first one, it triggers this transition waves. And just examples of use of these transition waves. So they have been used for energy harvesting to do some mechanical logic, some gates and an OR gates or NOR gates, reconfiguring samples, deploying structures. They have been used in several applications like that. So what we've done, yes, maybe just another example of some use of these waves. If you clamp a beam like that and you design it a certain way, you can, when the transition wave is excited, it can make some big movements. You can reconfigure a complex system with one impact, some location, and also like harness the velocity at which this transition waves travel in like almost 3D system here. So these are simulations based on the first example I showed you. We have not realized that experimentally yet, but maybe we won't. But what I'm interested in these days is to trigger these transition waves in a more subtle manner, more controlled manner, right? All the works, all the studies on these transition waves assume direct triggering of these transition waves from one boundary, and then propagation is observed. So, but the question we asked recently is, can we trigger these transition waves by using other waves that collide somewhere in the system and overpass the threshold to trigger this transition wave? So that was one challenge that we tackled 2 years ago. So we chose this platform, which was developed in the group of Jordan and René at UPenn, and this is a quasi-1D system of rotating squares once again. But the difference is that there are magnets embedded in these squares, so it makes each unit of 4 squares tri-stable. It can be a line like that, or it can be closed in one way or closed the other way. So there are like 3 equilibrium points. What we did is actually to start from this one and look at the transition waves transitioning to the right one. So this is a transition wave, an example of a transition wave that was studied before, just to show you that it can propagate in the system. You trigger it, and there is this phase transformation propagating. So just to have a look to what sort of waves can propagate in there, we did some numerical analysis of this system that we know how to model finely. And so we have this tri-stable potential. When we excite one chain like that with a weak amplitude pulse, very weak, we assume that we stay in the central potential well of the system, and we won't explore this potential energy further. And what we see here when we look at the space-time diagrams of the angle or the strain displacement difference in the system, we see waves propagating barely. They propagate, and there are also like wrinkles showing dispersion of the pulse. If we excite a bit stronger, we start to feel the nonlinearity of the potential in the system. And what we see is not only the linear waves in the systems that are propagating faster, but also stable structures of larger amplitudes. And these are the vector solitons. This is the vector solitons that I was talking about. What we can see is that actually this pulse is actually overlapping this one, so there is a strong coupling between angle and strain or displacement, which is not the case for the linear waves that don't propagate at the same. The linear modes don't propagate at the same velocity for each degree of freedom. And if we go even stronger, very strong on the system, then we trigger a transition wave. So we push the system in the other well, and we have these transition waves with a final state which is different from the initial one. So what about exciting these waves here that do not change the state of the system from both ends of the chain, and see at which amplitude we can maybe go and explore the other well upon collision. So this is this schematically what we do like that. We excite an impact from the left, from the right. Each impact is not enough to change the state of the system, but when they collide, can we do that? So once again, numerically, we can easily look at that. So if we are like too low amplitude, the two pulses, they propagate in the system, they cross, interact maybe, and then they emerge from this collision. But if we excite stronger, then when they collide, they pass the energy barrier necessary to go to the next state. And then we have a transition wave, which is excited. So this is only numerical. What we observed is numerically is that there is a threshold for that. If we take the two same amplitude pulses, increase progressively amplitude, above a threshold, we always trigger a transition wave, and below that, we never trigger a transition wave. Of course, we can change the characteristics of the pulse that we excite from each side, and then there is a rich collision behavior and rich output behavior. So the experiment is tricky. It's not very easy. The structure is not very stable. So you can have bending in the other directions. But these are two impactors here that you have to excite at the same time. This is the sample, which is tri-stable. And okay, you have to trigger the pulses at the same time with the same amplitude and so on. So this is typically the experiment. So the tracking of the experiment is here. They're a bit noisy. You have the movie at the top. What you see is two pulses propagating barely. We see them better maybe with the movie. And when they cross and collide here, they change the state of the stable state of the chain, and this transition wave is then reconfiguring the whole sample. So what you see is that the first units on the left and on the right, the left and right are not closed. It's because we remove the magnets from them in order to avoid direct triggering, which was happening all the time, direct triggering of the transition waves when we would impact them. But the rest of the chain is reconfigured and tri-stable. Okay, this is a final view of the experiment. So we have the two pulses propagating. This is experimental and triggering the transition waves. So we could somehow demonstrate experimentally, but mostly numerically, this effect. And we looked at it in the two dimensions, actually, in the same setup that we studied for vector solitons. And this is even richer, of course. You can play with the time delay in numerics. You can play with the orientation of the collision of the pulses. And of course, we have the same qualitative observations, such that there is a threshold above which we trigger the transition wave and below which we don't. Yeah, so there is also a critical size that should be initiated for the transition waves to propagate. Another example is this. You can change the time delay between the two pulses and trigger transition waves at a different location. You can change your orientation as well. And it changes the sequence of the transition wave propagation. Finally, just to mention it, this is something we'll submit soon. We started to be interested in a 1D system to other types of waves that can be put in collision to trigger transition waves. We knew that these systems support also discrete breathers, which are these types of waves, so fastly oscillating in time waves, but long wavelength in the system. So it's a quasi-1D system here. It's numerical only, and these waves look like this when they are triggered from both sides of a 64-element system. So they oscillate fast, but they actually they are like more or less long wavelength in the system. And if you just change by 2 elements the thing, but trigger exactly the same pulses, since they are oscillating fast, the exact phase at the collision point is a key element to the triggering or not of the transition wave. So in one case, it's triggered. In the other case, it's not triggered. You have the spatial-temporal plots here. And so we studied all the conditions for these breathers to trigger or not these transition waves, and this is very rich, actually. Unfortunately, I don't think in experiments it will be realistic to do that, because I mean, it's too long of too many oscillations, too much damping in these flexible structures that would not allow for these waves to survive. Although we've studied the effect of dissipation, and reasonable dissipation works actually. And you can go to some very complex collision scenarios where you can trigger 2 transition waves, for instance, at 2 different time and locations in the system. Well, this is the type of things that are like interesting to us. Recently, we are also interested in since these systems are multi-stable, they contain multi-stable units. These bistable units can be seen as memory bits, actually. They store memory. And so using nonlinear waves, these waves to read, write, erase memory in a system in a smart manner is something that is really exciting to us right now. We have a graduate student working on that, Audrey Watkins at Harvard. Okay, last quick part of my presentation. So far we have dealt with finite systems, but inside they were periodic. So we can model them, we can write the equations of motion easily. They are all the same for each unit, except the boundary one. So it's very, let's say, we can deal with that, and we can go to analytical solutions even sometime. What about nonlinear, non-periodic systems? And that can offer obviously more possibilities, but are like harder to design. So to do that, the main player is a postdoc right now at the Bertoli Group, Giovanni Bordiga. We developed a framework, a computational framework, actually, to be able to solve the propagation problem in a very similar systems than the rotating square structures, but with arbitrary shape or almost arbitrary shape units connected by soft ligaments to the next neighbors. And that's what we call the differentiable mechanical metamaterials. And I will tell you a bit about that because I think it's very interesting. So, okay, if we consider a system like that, 2D, similar to the rotating stress structure, we can actually write the problem with Lagrange equations. We go to the motion equations, let's say, but we can keep the Lagrange so that we have the energies in kinetic energy and potential energy that are like our initial like quantities. And then with this equation in hand, we can solve a forward problem. So imagine you impact something here, you have a dynamic wave problem, the dynamic problem to solve. You can solve it by integrating these equations, right? So thanks to a nice Python toolbox, JAX, these equations can be actually differentiated. The results of these equations of the simulation can be differentiated relative to any parameter of the system numerically. So we can know if we change the mass of this thing or the one vertex position of this thing, we know what is the result, what is the effect on the result, without necessarily running many simulations. And this can be done relative to the geometric parameters, the coupling parameters, the damping, the initial conditions, etc. So all these gradients can be very efficiently calculated, and it helps, of course, to optimize the result that we want to have. So this is how these non-periodic metamaterials are like designed. We have the framework to describe the dynamics in there, and to see what sort of change what will it do on the results. So let's consider a problem that we considered actually. Imagine we excite this input region, the two units, with a pulse, which is this type. We define it, and we want to focus the kinetic energy at the maximum of kinetic energy here in these 4 units. This is what we want to do, and we want to change the geometry of the system to achieve this goal. So it's not an obvious task if you think of it. You might have some few intuition. You might think, okay, I don't know, let's make a sort of waveguide here, or resonance here, maybe, I don't know. But it's not easy to know, to define the geometry, right? So there is a cost function. We want to maximize the kinetic energy in this region. We have clamp corners in order to think of like future experiments. And okay, let's see. The design variables are the positions of each of the vertex of each of the units, with some constraints of non-overlap and etc. Of course. So when we do an optimization run of this, it looks like this. So okay, after a few iterations, you want no overlap, you want the maximum energy focused, and you end up with a design which is like this, and not more evolving after like 68 iterations. Not that one iteration takes maybe, I don't know, a fraction of a second, so it's very, very fast. So okay, we have this design. So what we did is to fabricate it and test it experimentally. So we have a low frequency shaker here, inputting something not too far from the signal used for the optimization in numerics. So okay, we can change, of course, the parameters of the signal, and we take a movie of this experiment to see what happens. So this is typically what happens. So this is the experiment. This is the simulation for the optimal case, and they are more or less synchronized. You see the large displacements. It's very large amplitude. It's nonlinear, and you see what happens. Most of this like bigger masses is like moving a lot and almost resonating. There are structures that are like with some more alignments here, but it's very difficult to. No one could have guessed this exact design without the computer. And when we look at it, we can look at the kinetic energy, peak kinetic energy along a line, for instance, and we see that for these 2 units, we have a well-focused kinetic energy. And it's not only coming from the bigger masses, it's also the higher velocity, of course. Okay, so then we can go to more advanced problems, maybe, that we are in the process of testing experimentally, but these aren't just numerical results. So we said, okay, we have a system. We want to focus at 2 different target regions. One being focused here when we have a complex strain of 2%, and if we apply a larger strain, we want the focal point to be here. And with this constraint, it's actually worked to some extent. So with one compressive strain, we have focusing here. When we go to 5%, focusing is mostly in this region. And maybe the last example I want to give is this one. So we have one focal region for one compressive strain. Same impact here. We want to focus here. And then upon like larger static strain, we want to protect this region, or like have the minimal kinetic energy. So once again, when we excite, we have a large kinetic energy in the region, and then with the larger compressive strain, we see that it moves much less, mostly because all this part behind the target point is jammed. The units are contacting, and they cannot really move anymore. Okay, and this is the plot showing. So that's basically what I wanted to share with you. And to conclude, maybe for the takeaway message, I would like to remind that, or to say that this flexible mechanical metamaterials that we studied, this type of this platform is actually very rich for nonlinear waves. The nonlinearity is of a geometrical origin, and it's coming from mostly the rotation of the units, and we can design it. And we have, like, in mind many other applications, things to test with these systems for vibration control, locomotion. I told you about mechanical logics or memory, and reconfiguration of systems. And I would like to acknowledge the people I work with on these topics, from some of them from Le Mans, Paris, the Jordan Ranel's group, and Katia Patouli's group. Thank you very much.
Thank you, Professor Tournat, for this nice presentation about nonlinear elastic materials. So if you have any questions, feel free to ask.
Is vibration, localization, and issue, like particularly in 1D, if you have manufacturing defects.
So is the vibration localized at sorry, I didn't.
Periodic structure, it would say that you have some disorder, there can be some localization, can be. That an issue in your study?
It's not an issue. We haven't been able to observe that. I think this could be a very interesting thing to look at, because obviously our systems are nonlinear. So on this localization in disordered and nonlinear systems is like an interesting topic. Rather fundamental, I would say. There are still very many open questions. So yeah, we haven't looked at that, and I don't think we've seen any of this in these experiments or in numerics. Yeah.
Thank you.
Repeat the question so that people.
Okay.
So, general question, does the nonlinearity of the system enable sharper control than an analogous system that was purely linear would?
So the question is, does the nonlinearity of the system enable sharper control that it could, like, exist in the equivalent linear system, you mean? Yeah. So yeah, this is interesting. This is interesting. I think that by the fact that these systems support nonlinear waves that are not supported by linear systems, such as these stable solitons, or these breathers, or these transition waves. All these waves are nonlinear. They come from the nonlinearity of the system. I think that many of the things I've presented would not be even like possible or observed in the equivalent linear system. So yes, my answer is yes. We would not be able to observe any of this. Concerning the control, I mean, we all know that most of the work on phononic crystals, architected structures, metamaterials, is done in the linear domain. So there is a lot already done. It's very good for controlling waves and so on. I think that going nonlinear, large deformations, nonlinear waves, it's not necessarily sharper, better, but it brings new ways of controlling new waves. So it's really, I don't know if we can compare the quality of the control that we can have, but it's on different objects, and it's of course with different methods that we can do that. Yeah. Does it answer the question? Yeah.
Is the configuration changing classes reversible, like from closed to open configuration?
Yeah, when we speak about this, for instance, let's say, let me see. Yeah. So it depends on the potential, bistable potential. So if we consider a system without any damping, with equal potential well level, so symmetric potential well, then it's possible. It's reversible. As soon as there is damping, and it's the case in reality, then you need to add somehow some energy to the system, or to provide energy to the system. So if it's through an impact, you can go from one way to from one to another, and if you provide another impact, it can go to the other state. However, these systems, for instance, they have like different potentials, and we can only go from the higher energy level to the lower one, because of damping there is energy loss, and you need to provide energy to the system, to the wave, so that it can propagate. So which is interesting is that this system can carry transition waves forever, even if there is damping, because energy is stored and is released each time a unit is changing state. So yes, there are very different physics between symmetric wells or asymmetric wells. In this case, for instance, it's not a propagation equation; it's a nonlinear diffusion equation, reaction diffusion equation. So it's very different, but it propagates. So of course, yeah.
The 2D soliton experiments that you go to the video, it seems like there's something underneath the structure. The granular suit.
The movie, this one, yeah.
It's like you have granulars on the. What is the reason?
Okay, so this material here is PGMS. It's very sticky. If you put it on a table, it won't move. It's like yeah. So the trick we used, and it works well, although we don't really know to which extent it affects the results. With inertial effects and so on, but we've put like centimeter size metallic beads, a bed of these beads, and it seems like for this experiment, at least, when you have a single impact, it makes the sample like kind of free to move and so on. If we would like use, I guess, like sine wave excitation, something like that, I would prefer to maybe hang the sample in air or something. But for pulse, it's reasonable. For some experiments, if you need to avoid like coupling or friction with us, it works well, I think.
For the energy focusing with non-periodic designs, do you expect similar effects if you move to more rigid materials?
Good question. So I don't know if you've noticed, but I think I mentioned it. These things are deforming strongly, right? When we look at one experiment like this, the deformation. This is experiment, right? We look. This is big displacement, big strain. So obviously, in a more rigid, I don't know, 3D printed metallic structure like that, we won't see we won't see these displacements. And as the nonlinearity of the system is coming from these large amplitude displacements and rotations, I expect that there won't be much nonlinearity first in a more rigid system. And second, I guess in principle, it works in nonlinear regimes, this optimization. So I guess it will find some structure that that can focus kinetic energy for a linear system with a small amplitudes. So maybe this process, this framework would work for linear waves, but yes, it will be, yeah, not nonlinear waves, let's say. Yeah. Yeah, sorry. Yeah.
Is it possible to propagate this soliton waves when you have a material
Yes, it has been shown. I don't have a recent examples in mind, but yes, nonlinear material nonlinearity is. So, for instance, if you take a waveguide, an acoustic waveguide, air, you use just the nonlinearity of air, and you induce some periodicity in the system by changing sections maybe of the waveguide. Then by doing that, you have some dispersion in the system. Then this system supports solitons, because of the nonlinearity of air and the periodicity inducing dispersion, which are dispersion and nonlinearity, the two necessary ingredients for solitons. So yes. But once again, you cannot change like this the nonlinearity of air. So while you can change the dispersive properties by changing the waveguide like shape, and what the whole point of like doing this is that we can actually change the nonlinearity of the system, which is geometric, but we can change it.
If the material used to build the structure is changed, given like different or Poisson ratio, do you expect the effect to be linear, or is it a whole different situation?
Yes, that's so there are mainly two materials in these systems, for instance. There is this, I mean, the red, dark red that we see, which is the rigid mass. So for this, changing the elasticity will not change anything. We assume that and it's the case even in experiments, that it doesn't deform. It's not. But the shims that connect this, so we see them better here for the schematics, but the shim that connects this rigid masses, they have some properties. So if you take like thicker shims, you change the material, longer shims, it changes obviously the couplings and the elasticity of the whole structure. Yeah. So, and what are the effects on that? I mean, right now we have changed only the geometry because it's the simplest. And in numerics and in experiments, I mean, we don't want to change by a factor of 10% or 20% the elasticity. We have to know I mean, it's a whole different work to change that. Here we just have to use the same shims everywhere, but change the geometry of the units. So that will be another, I guess, parameter that could be used to optimize even further the structure. Yeah, that's if you're able to fabricate it to demonstrate it experimentally, then yeah, why not?
Any other questions? Let's thank again our speaker.
Thank you. Thank you.
We close this seminar. Thank you very much for being here.